Hello, everyone. Welcome back to another video with us here at LMDN STEM Academy. Today, we will be discussing empirical and molecular formulae and just how you can be able to always deduce the empirical and molecular formulae of compounds. So let's get into it. So we'll start by comparing and contrasting the empirical formula with the molecular formula. So the empirical formula is the simplest whole number ratio of atoms in a compound, right? While the molecular formula is the actual total number of each atom in a compound. And so let's take a quick example here. Let's look at your classic ionic compound, right? So let's imagine that we have an ionic compound such as NaCl. Right? So let's look at NaCl. So NaCl is an ionic compound. And the formula that we generally talk about for NaCl is just NaCl. And we can see here that that's the simplest whole number ratio of sodium to chlorine. And so what we will find is that for ionic compounds, the empirical formula, right, and the molecular formula are exactly the same. This is the lowest that the number of atoms can be, and that is the formula that we deduce naturally, okay, normally. All right, so that's an ionic compound there. Let's look at some covalent compounds now. So if we look at a covalent compound, such as water, right? So water is H2O. We don't know water to be anything else, right? And so the simplest whole number ratio is that there's a 2-to-1 of hydrogen atoms to oxygen atoms. That's the simplest ratio. So that would be the empirical formula of water. And it's also the molecular formula of water, right? So what we're seeing here is that there are certain compounds that have the same empirical formula and the exact same molecular formula. Now let's look at a case in which they are different, because those are the cases that we will encounter more often than not when we're given these questions. So let's look at hydrogen peroxide. So hydrogen peroxide is HO, right? And that is its empirical formula. But the molecular formula of peroxide is actually H2O2, right? So you see that in this case, this is the lowest whole number ratio. And in this case, it's like the actual atoms for the molecular formula. We can simplify that. And then we do that. What do we get? HO, right? So that's the difference between the empirical and the molecular formula. And if we look at this, right? In order to have gone from the molecular formula to the empirical formula, we see that we divided both numbers here through by 2. So that there's a connection then if we were to go the other way from the empirical over to the molecular, in that what would we have done? We would have had to multiply by 2. So there's a factor that connects the empirical formula to the molecular formula whenever it is that they're different, right? And we'll come back to this idea later on. So let's take a few more examples of cases where the empirical and the molecular formula is different. So let's look at benzene. So the empirical formula of benzene is actually, let's put it up here. The empirical formula of benzene is actually CH. But the molecular formula of benzene is actually C6H6, right? So this is the actual number of atoms that's in that benzene ring, and we're very familiar with that. But the empirical formula, which is the lowest, the simplest whole number ratio, would just be CH, and we would have gotten it here by dividing these two through by 6. So that's how we ended up here, right? To connect them, there's a factor, and that's a factor of 6. So if I were to multiply this guy by 6, I would end up getting this. And if I were to divide this molecular formula by 6, I would have ended up back here. So the key takeaway here is that the empirical and the molecular formula are different things. There are instances in which they can be the same, and that's when we have ionic compounds generally, and in covalent compounds such as water, they're the same. But generally, they are different and they will be connected by a factor, right? A whole number factor. All right. So now that we're clear on what empirical formula is and what a molecular formula is, then we can start our discussion as to what it is exactly that we're doing when we're being asked to determine an empirical formula, right? So to determine an empirical formula, we may be given the mass of each element in the compound, or we may be given the percentage by mass of each element in the compound. So when I say we may be given the mass of each element in the compound, you might have a situation in which you're told that there is 1.24 grams of carbon in a compound. And in that same compound, you perhaps maybe have hydrogen, and they'll tell you that you have 2 grams of hydrogen that makes up that compound, and so on and so forth. From a percentage by mass standpoint, they may tell you that you have 10% carbon, and then the rest of it is hydrogen, right? So just from a percentage standpoint, just imagine that they gave you a percentage of how much of the element is present. So these are the kinds of information that we will be given. And then from here, we are going to be expected to determine the empirical formula. So let's talk about how we might go about doing that, right? So the key thing here, the overarching thing for us to remember is that the main goal of determining an empirical formula is that what we're really trying to do is we're trying to get to the lowest whole number ratio of the atoms that are present in that compound, right? And so really what we're trying to do is figure out the number of moles then, right, of each element that's present. And then once we get the number of moles of each element that's present, then we divide those moles by the lowest number of the moles that we obtain, because remember now it's an empirical formula, so we want the lowest possible whole number ratio. And then finally, we'll put everything together, right? So first step, convert mass to moles. And why might we do that? Why might we want to do that? It's because when we look at a formula, right? So for example, let's look at C2H6, right? So that's ethane. If we look at ethane, what this formula actually tells us is that in 1 mole, in 1 mole of ethane, so in 1 mole of C2H6, what it's saying is that in 1 mole of C2H6, there are actually 2 moles of carbon, as indicated by that 2, and there are 6 moles of hydrogen, as indicated by that 6. And so whenever they give us a mass, we want to convert that to moles so that immediately we'll know what these numbers should be, right? But then the next step where we're dividing it is so that we can get the lowest whole number ratio, which is what we're after in an empirical formula case, right? Now, it is important to know that in the empirical formula case, because it's an empirical formula, it's derived from experimental data, right? So what that means is that we might have a sample that's not equivalent to like what the full molar mass or a mole of the sample would be. And so because it's an experimental amount of mass, like a smaller sample of the larger compound that we have, when we find the moles in the empirical case, it's not going to be the actual number of atoms. It's an empirical number. And so that's why the empirical formula in some cases would turn out to be different from a molecular formula. And we'll bring this up a little bit more later on, but it's important to note at this point, that the moles that we get are reflective of that experimental sample that we used, right, to deduce that. So let's go on now and let's take an example here. So let's move forward and take an example. So here's an example now. So we're determining empirical formula and we're using the scenario, right? We're taking a scenario and we're given the mass of each element in the compound. So here's an example. The foul odor of dirty socks may be attributed to caproic acid, which is an organic acid made of carbon, hydrogen, and oxygen. The results of combustion of a 0.45 gram sample of caproic acid indicates that it contains 0.279 grams of carbon, 0.0467 grams of hydrogen, and 0.124 grams of oxygen. And so given all of this information, they want us to calculate the empirical formula, right? So this is a combustion. So we're taking a sample here and we're combusting it. So we are reacting it with oxygen. And so we end up getting these masses, right, in the end. And so let's go to our step one, as we just discussed. In step one, we are going to convert the masses, the given mass of each element, to moles. Why are we doing that? Because ultimately the mole is going to tell us the exact or how much atoms, right, of the corresponding elements are present in this sample, right? So let's start with carbon here. So if we take carbon, what did they tell us? They told us that we have 0.279 grams of that as a result of the combustion. We know that the molar mass of carbon is 12 grams per mole, right? And so if we want to find the number of moles, what are we going to do? Number of moles, we want to find the number of moles of carbon. Right, the number of moles of carbon. So I'm just going to put a little n actually to save some space. So the little n represents the number of moles of carbon, and I'm going to put a little c to denote that it's for carbon. And that's going to be found by dividing the mass that they gave us, the 2.79 grams, 0.279 grams, and I'm going to divide that by the 12 gram per mole, right? Because to find moles, we do mass divided by molar mass. The grams cancel, the moles comes up top, and the number that we will get there for carbon is that there are 0.02325 moles of carbon based on the mass here. We do the same thing for hydrogen. Hydrogen, they told us, is 0.0467 grams of it. And we know hydrogen has a molar mass of 1 gram per mole. And so to find the moles of hydrogen, we're going to do 0.0467 gram divided by 1 gram per mole, because that's a molar mass, right? Grams cancel, mole comes up top, and we are left with 0.0467 moles, right, for hydrogen. For oxygen now, they told us that the mass that we got from combustion was 0.124 grams. We know that the molar mass of oxygen is 16 grams per mole. And so we're going to find the moles of oxygen by dividing the mass that they gave us, 0.124 grams, by its molar mass, which is 16 grams per mole. And when we do that, as usual, the grams go away and we are left with the mole, which comes up top, which is just going to end up to be 0.00775 moles. All right, so we're done with step one. We've successfully converted all our masses to moles. So we're done with step one. In the second step now, because it's an empirical formula, we want to divide the moles of each element that we got here by the lowest number of moles, right? And so that way we're going to get the lowest, the simplest whole number ratio. So of all of these numbers, let's look at them. Let's look at these numbers here. 0.0235, 0.0467, and 0.0075. We see that this is the smallest of all of them. So this number here is the smallest of what we got from step 1. And so what we're going to do, we're going to divide all of these moles by that smallest moles. And we're going to divide it by itself as well, right? Because it is corresponding to an element. So for carbon, the lowest number for carbon that we're going to get is we're going to do 0.02325. We're going to divide that by the 0.00775. And that's going to get us 3, right? And then hydrogen now, we are going to take that moles that we got from step 1, 0.0467, and we're going to divide that through by the lowest, which is 0.00775, and that's going to get us 6, right? And then for oxygen, of course, because oxygen was the lowest number of moles, which is 0.00775, and we are dividing that by itself because that was the smallest number. We're gonna just get 1 in this instant, right? So now we have the lowest number. We have the lowest whole number ratios here. It's 3 to 6 to 1. And so now we're ready to write the formula. So we write the formula for step 3, showing the simplest ratio. So the formula will be, let me change my color now. So it's going to be C3H6O. So that's our empirical formula, okay? So each time, we're just going to follow this approach when we're given mass of going from mass to moles, and then we're going to divide by the lowest number of moles, and then finally put it all together. Okay, so let's take another example. Let us take the case in which we are given the percentage by mass of each element in the compound. Right? So this is our second kind of data that we might be given. So in this particular case now, here's our example. We are given a chloroalkane, right? So that's an alkane that contains a chloro group. And the question says that this chloroalkane has 24.24% carbon, 4.04% hydrogen, and 71.27% chlorine. They're asking, what is the empirical formula of that compound? Okay, so we're given percentage by mass. We need to go to the empirical formula from that point. So the key assumption, right, whenever we're doing a percentage by mass calculation, the key assumption is that there's a sample of total mass 100 grams, right? So you can imagine that if we make an assumption, if we assume that it is 100-gram sample, right? Then if I told you that of that 100-gram sample, 24.24% is carbon, right? That's literally saying 24.24%, right, of 100 is carbon. And so you see that the 100s cancel, and what we end up with is that this is what? The equivalent of 24.24 grams of carbon, right? So when we make the assumption that the total mass of the sample that was broken down was 100 grams, we can immediately see that the percentages that they give us is equivalent to the mass of each element. Okay, and so we can rewrite this then as 24.24 grams of carbon, right? And we can rewrite this then as 4.04 grams of hydrogen. And similarly, this will be 71.27 0.27 grams of chlorine. And so now you realize that we're back in a situation where we have masses that we can then work with, okay? So here we are now. We're going to focus on carbon first. So here is carbon. So we found that the mass, by making this assumption, we found that that's a mass of 24.24 grams. We know that the molar mass of carbon is 12 grams per mole. So immediately we can convert that mass to moles. So I'm going to put NC, which is the number of moles of carbon, is going to be equal to 24.24 grams divided by 12 gram per mole. When we do that, moles cancel. The grams cancel rather. We bring the mole up top and we're going to end up with 1.006 moles of carbon from that step. And then for hydrogen, we're going to do a similar thing where the mass is 4.04 grams, and we know the molar mass is 1 gram per mole. And so to find the number of moles, we can do 4.04 grams divided by 1 gram per mole, right? Or grams cancel. The mole unit comes up top, and we're left with that being 4.04 moles. And we're going to do a similar thing for chlorine finally, which we know we have 71.27 grams of, and we know that the molar mass of a chlorine atom is 35.5 gram per mole. So to find the moles, we're going to divide the mass by the molar mass. So that would be 71.27 grams divided by 35.5 grams per mole. Grams cancel, mole comes up top, and we are left with, in this instant, 2.007 moles of chlorine. Right. So we are done with step 1. We're on to step 2. What is step 2? Is that we're going to have to divide the moles that we obtained up here by the smallest of them. Which one is the smallest of them? Let's look at the numbers. 1.006, 4.04, and 2.007. The smallest is going to be which guy? Actually, this is not 1 actually. This is 2.02. So let's correct that before we go any further. So the 24.24 divided by 12 is actually 2.02 moles. All right, so let's look at all the numbers that we have now. We have 2.02 moles, we have 4.04 moles, and we have a 2.007 moles. So out of all of these numbers, this guy is going to be our smallest one, right? So this is our smallest. So I'm just going to point to that so that we're all on the same page. That's the smallest number of moles that we had gotten from this conversion step. And so we're going to divide all of these moles individually by the smallest one. And so for carbon, we're going to divide 2.02 moles by the 2.007 moles. And so the net result of that is going to be approximately 1, right? So for hydrogen, when we divide it for hydrogen now, it's going to be 4.04 moles that we are dividing by the 2.007 moles. And so that will be roughly 2.0129. And then finally for chlorine, that was the lowest number. So we're going to divide it by itself, okay? So we're going to do 2.007 moles divided by 2.007 moles, and that will give us 1. Okay, so look, these are our simplest whole number ratio. It's a 1 to 2 to 1. And so we're going to write the formula, just putting these numbers beside their respective elements. And so it will be that our answer is CH2, because the 2 goes with the H, and then the Cl. There's only one of them. So our empirical formula then is CH2Cl. And we are done. We were able to go successfully from a percentage by mass data to our empirical formula by making this key assumption that we have a sample of 100 grams, and then we just convert the masses to moles and then finding the lowest, simplest whole number ratio, okay? So that's how we would approach it when we're given a percentage by mass. So let's move on. Let's take it a little bit further now. So let's look at the case in which we're determining a molecular formula, right? Now, there are two key pieces of data that you may be given, right? One or the other. You may be expected to go from an empirical formula to a molecular formula. And so that's kind of the case that we just did. You would have found an empirical formula, and then you're going to convert that to a molecular formula. And we spoke about this earlier, that there's a conversion factor that you can use to go between both of them. And we'll talk about that in more detail. So that's one kind of approach that you might be needed or asked to take to find a molecular formula. And the second approach is that you may be asked to go from volumes of gases obtained from combustion. And in this case, we would apply Avogadro's law. Right? So let's look at the first scenario first, where we're going from an empirical formula and we're asked to find a molecular formula from that. All right. So here's a formula that we can use to connect the empirical formula and the molecular formula. So generally, right, what you will be given if you're asked to find the molecular formula is that you would have had your empirical formula that you deduced, right, from the mass data or the percentage by mass data. But along with that, you'll be given this key piece of information. You'll be given a molecular formula mass of the compound in question, or they might just phrase it as a molar mass. Those two things we can use interchangeably, right? So you'll be given a molar mass of the compound, but you won't be given the molecular formula. So you will have to find that, okay? So we're given a molecular formula mass or a molar mass, and we can find our empirical formula mass, right? So if you know the empirical formula of a compound, so say you found the empirical formula to be CH, you can find the empirical formula mass. So we're going to write EFM, and that empirical formula mass will just be by you summing up these molar masses or these relative atomic masses. So it would be 12 plus 1 in this case, right? And so the empirical formula mass would be 13. So we can always find an empirical formula mass as long as we have an empirical formula, okay? So then we can take the molar mass that will be given to us in the question and divide that by the empirical formula mass that we're able to deduce, and we'll get a factor n, right? So this factor n is a factor that connects the empirical formula to the molecular formula. And we saw glimpses of this early on, right? That there's a factor that connects the two things. And so once you have your empirical formula, which you would have deduced first and foremost, and you were able to get this n, then right away, we'll have our molecular formula, right? So that's how we do this kind of conversion. Now we're going to see this in practice. So let's take an example of this. So let's move forward, right? So let's take an example. And what we're going to do is we're going to take the very first example that we did and just extend that question a little bit to include molecular formulas. So again, we have the foul odor of dirty socks can be attributed to caproic acid. We have the results of a combustion. They gave us the masses, right? So these were the masses of each element that we had. And then we are now given this additional key piece of information, which is the molar mass, right? Which we didn't have before. So now we have the molar mass, and they want us to find the molecular formula. Now remember, we already calculated the empirical formula earlier in this session of caproic acid. And what did we say that was? We said that that was C3H6O. All right, so the very first thing I have to do is find the empirical formula mass, because this is the formula that we're using, right? We're connecting the two things together. We are doing that the empirical formula times that factor n, which is ultimately what we seek, is equal to the molecular formula. And to find n, we have to do the molecular formula mass, or the molar mass. We have to divide that by the empirical formula mass. All right, so remember those key equations. So we have to find the empirical formula mass. We have the empirical formula. So to do that, what are we going to do? We're going to say 3 times the relative atomic mass of carbon, which is 12, plus 6 times the relative atomic mass of hydrogen, which is 1, plus, because there's only one oxygen now, it's going to be plus 16. When we add that all together, we are going to get that that is 56, right? So remember now we want to find this factor n. So what are we going to do? We're going to say the molar mass that they gave us, which was 116 gram per mole. We're going to divide that by the empirical formula mass that we just calculated and found to be 58 gram per mole. So we're going to divide those two things by each other to get our factor n. And so those units cancel and we are left with 2. So our factor that connects our empirical formula to our molecular formula is 2. So to find the molecular formula, we're going to apply this formula now, right? Where we do the empirical formula, which was C3H6O. We're going to multiply all of those by 2, right? Multiply all the number of atoms that were there by 2. And so now we'll end up with the molecular formula, which is C6H12O2. Okay? So remember now, if we have an empirical formula, we can find its empirical formula mass. Then we can find a factor by bringing in the molar mass and then dividing that by the empirical formula mass to find that factor. Once we get that factor, we can multiply our empirical formula by that factor to finally get our molecular formula. Okay? All right. So let's take another example of this using an example that we did earlier, but just extending it. So here's another example here, right? We're looking at our chloroalkane again. We got the empirical formula from our previous work on this question, and we got that empirical formula to be CH2Cl, right? So what are we going to do first and foremost? We're going to find our empirical formula mass. We're just going to add up all of these, right? All of the relative atomic masses that we get from this compound. So that would be for the carbon, it's 12 that we are adding to 2 hydrogen. So it will be 2 times 1 plus the carbon, which is 35.5. So that empirical formula mass will be 49.5 grams. Now remember, we are expected to find the molecular formula in this case. We are given a molar mass because we can't proceed without that, right? So they gave us a molar mass. So all that we have to do to find the factor that connects the empirical formula to the molecular formula is divide the molar mass that they gave us, 99 gram per mole, we're going to divide that by our empirical formula mass here. So that will be 49.5 gram per mole. And that will be, we cancel those two, and we are left with a factor that connects them, a factor of 2. Okay? So finally, what we're going to do is we're going to multiply our empirical formula by that factor. So it will be CH2Cl times 2. And that will get us, we're going to multiply every atom by this number. So it will be C2H4Cl2. All right, so that then is our molecular formula. And so with that, we're going to end this lesson here, and then we will reconvene in part 2 to discuss how it is that we would go from some volume of gases data, which was the other case. We're going to talk about how we go from volume of gases to find the molecular formula. So please be sure that you subscribe to this channel, hit the notification button, and then you will be notified as soon as part 2 is added, okay? So just one more piece left in our completion of figuring out molecular formula. So please be sure to subscribe, and we'll see you again soon. Thank you for watching.